first turn off Sprite Dma, and then we'll have some fun and display some sprites. Now, the easy way, I hope I can display this. As you could see there, and as you could see in our previous lessons, you could see a quick glimpse of a red sprite there. The reason it's red is probably because my mouse pointer colors are set to red in preferences. And the reason we get trash there is because Sprite Dma can be turned on and off several times during the display of a frame, and so that's nothing special, and that means that if we leave it on, we don't know where it will point to. We haven't done anything about the DMA control. That means that our DMA control is set to whatever value it has in the in the operating system. Currently, as you can see, the operating system is displaying a bitplane DMA. It is also displaying Sprite Dma in the form of this pointer, and likely also disk DMA is enabled, and so on. And to turn off all DMA completely, we do the same as we did for the interrupts. I will now show you a good practice, and that is to also disable interrupt requests. This is not related to DMA at all, just good practice, and we do it twice to be good boys and be compatible with Amiga 4000 computers who has a hardware bug. But in the same fashion, we can turn off all DMA, including copper DMA, by writing to dma-con, as explained in previous tutorials. That we must at least enable copper DMA. I usually do it this way. I'm sorry. Well, it's not magic. This special value enables all the usual DMA that you want to have in a demo, unless you're loading from disk. It enables bitplane, sprite, etc. DMA, and lets the music player initialize the audio DMA if it needs to save away the value of the the original value of DMA-con. Now, as I said, there are two versions of each of these control registers, and the read version of this address is this address, so that we can move the contents, the word inside this address. Remember that all custom chip registers are word access only, although you can get away with byte accesses and bit tests in some cases. And we'll move this to data register 3, which I suspect is free. I will check this in a moment. And I'll do this by searching for D3, and also I will search for exit, and here's where we might and I will show you now the trick, namely that in this case we had to OR the interrupt enable bits, because there was bit 14, which was another bit that enabled all of the below bits. There is a similar bit in DMA-con, and it's bit 9, so that we must OR with a different value to this register, and Move that to the Dma register. And just in case we turned on any interrupts, that any DMA channels that weren't on for the operating systems, we should clear it first, so that we will repeat the clear operation like this. We can even put it like this. Well, it's neater that way. And thereby we have made sure that we have restored the bits in this register exactly as they were when we entered. So that's it. If we run this now, it should be business as usual. It seems so. And as you can see, if you in previous tutorials didn't get your pointer back, you could get it back by doing this. But we don't need to do that now, because we've been good boys and programmed everything system friendlily. So that covers the Dma bits. If you wish to find out what each bit does, you can Google Dma, and you will likely end up at winicky.net, which is a nice site, which will also tell you about any additional bits that are used on the ECS and HEA chipsets. The bit in question that we are interested in is Sprite Dma, which should be enabled here. Let's check that out. No, it is not. So no wonder we didn't get the sprite bug here. However, I suspect if we enable bit 5, this register, yes, you saw it there. So this is basically all you have to do, with some exceptions. We are lucky enough to have all the interrupts and interrupt requests disabled by the time we do this. However, it is good practice to wait to the vertical blank. Well, the general recommendation is to clear this bit in the vertical blank interval, which is not impossible, of course, but you can't wait for a raster position that is in the vertical blank, just as you can't wait for a horizontal raster position that is in the horizontal blanking period, simply because the raster is skipping, so that you can't match. It's simply skipping, so that and not reporting its position with fine enough granularity that you can rely on a wait raster to hit that position. Now, to fix this bug, as I said, just clear the bit. However, in some cases, such as if you don't want to disable all the bits in interrupt enable, because you want to load a file, for example, you're loading the graphics that is to be displayed on the bitmap instead of just filling it with random data as we did. Then you really should wait for the end of frame or start of frame before taking over the system. I prefer waiting for end of frame, because that ensures me that whatever is in the copper will antecede, will follow the hardware initialization here. And to do this, I've prepared a to make sure this clearing of the Sprite Dma bit works at all times, so that we should be good boys and wait until end of frame before we and we do this by simply moving some position. I prefer this position and the frame. Wait raster. And this is a routine that I've prepared in order to save you some boredom and unnecessary talking. And I will just explain it. Anyway, what it does is it reads a long word from this position, which is two custom chip registers, the vertical and horizontal position registers. And this is unfortunately placed in the memory so that you have to shift it and mask it and match it to the value that you put in D0. And this is what it does. Puts the mask in D2, shifts up the value that you specify, the line you want to wait for. It masks it by ANDing it. The AND operation leaves a 1 where there's a 1 in the first operand and a 1 in the second operand. Conversely, the OR operation leaves a 1 in the destination, which is D0 here. If there's a 1 in the source or a 1 in the destination, and that's how the digital logic works in the CPU. So that's a nice little tutorial there. And here we fetch both positions, vertical and horizontal position, which is contained in the lowest byte in the long word that we fetch here inside the loop, and that we put in D1. We mask this and compare this with the masked value in D0, the masked and shifted value in D0. And if it's not equal, then we branch back to wait raster. That's, well, it's not the optimal wait raster routine, but it works on all hardware and is short enough and easy enough to explain for our purposes. So that is an example of putting stuff in a in a subroutine and call it with BSR. I think that's the first time we've used branch to subroutine. Of course, this is equivalent. However, it wastes 2 bytes of code. We've used jump to subroutine before, and that's a long jump to a faraway address in memory. We don't need that here because wait raster is just down here, just maybe 50 bytes away from where you call it. So that we might even try a byte offset and save another 2 byte. So that's what we do. We wait for end of frame. And now, this method is guaranteed to get rid of the sprite flicker. That we wish to keep it on because we want to display some nice sprites, and it works the same way as, almost the same way as bitplane, as we did the bitplane, as we displayed the bitplane graphics data. This was the little loop that filled the bitplane with the graphics data that was to be displayed. And in just the same way, almost, we will point the Sprite Dma pointers to some address and make sure that that address contains the correct data for display, to be displayed. So the Sprite Dma pointers must be reset each frame. And the best way to do that, you could do it in the main loop and set them each frame. But just as we moved the color changes, which are also custom chip register modifications or pokes, we can poke the sprite registers in the copper as well. And we need to set them before the I'm getting a phone call. I'm pausing here. I have a small template here, which I will use. And this mask should explain the final byte of these two words. Now, we can divide these up to make them easier to read. And what you have here is the vertical start position, which is the same vertical start position as every other raster line in the system. That means that here you have the start of the screen vertically, and here you have, incidentally, the 2-pixel granularity DMA fetch start position, or left edge of the DMA portion of the screen. And this corresponds to exactly to the sprite values, so that if you want to put a sprite pretty high up, you would maybe put it at the very top of the screen. If you wanted to put it at the left edge, it becomes a little bit trickier. It's still 2-pixel granularity. However, you have to subtract 8. So that this puts it, I hope, at the left edge. I can never remember whether to add or subtract 8. And this is the stop position, and of course this must match the number of lines. You must take this value and add as many lines of graphics data as you have in your sprite, or else it will come out of sync. It would start reading data words as control words instead, and that means that if we were to put this at not position hex 3C, which is the stop position, but at 3B, then if we change this to something else, then it would read this 15th line as a control word and continue the sprite, likely. Now, the correct way is, of course, to add as many lines as you have graphics data to the vertical stop position, so that this vertical start byte corresponds to hex 2C, this corresponds to hex 30, and this corresponds to the vertical stop position, which is hex 3C at the top of the screen. And as you remembered with the raster position, it's 9-bit, and so is the vertical position for the vertical start and stop of the sprite, and so is the horizontal position of the sprite. It's also 9-bit, so that we need to put in some extra bits at the end of the control word. Now, this bit is called the attach bit, and it's currently set. We'll clear this last control byte. It's currently set. It should be cleared because we we don't combine two sprites into one. We have only one 2-bit plane sprite, which we want to display, and this then it makes it necessary to clear that bit. You would set it if you were to combine two sprites. We could, of course, make it a little bit easier by writing it this way, but this is a good way to exercise your binary skills. This bit is worth 1, this bit is worth 2, this bit is worth 4. That's all you need to know to solve this little mathematical puzzle. And what these letters mean is start, end, and horizontal. so that the bit number 2, third bit from the third least significant bit, is the 9th bit of the vertical start position. The next bit is the 9th bit of the vertical stop position, and the H bit is the least significant bit for the horizontal position. And this is what makes this 2-pixel granularity of the DMA adjustable, so that you can put the sprite at any horizontal pixel position you like. Simply because we've put it at the top of the screen, we need to set no bits in this last portion of the second control word, but we can leave it as it is. We do have to change this. Since we inserted a comma here, we need to make sure that the declaration matches the size of the data in the declaration. If we run this now, nothing should happen. If we set some pixel randomly in the middle, we should get a pixel in the left edge, near the left edge, about 7 pixels from the left edge of the screen, in some random color that we don't know, but is likely red, because I know that the mouse pointer uses the sprite 0. So that's it. Save this and run it, and we should see a red pixel at about 7 pixels from the top and about 7 pixels from the left. We do not. Okay, so I assume that I was wrong. I can never remember that. So this is very strange. It is right at the left edge. That's impossible. If we look at it again, we can see that it's perfectly aligned with the bitplane data, which is incorrect. Can verify this. Now I have 2 dots outside the bitplane data, and the only reason that this can be because Sprite DMA data cannot be displayed outside the display window is the scroll register. We haven't set that to a value. Shall we do that? We can set it here. It must have been initialized to a non-zero value. And now if we run this, the red dot should be 7 by 7 pixels into the screen. And it is. And as you may have noticed, we have sprite garbage. Now that's easier to explain. The reason is that we've turned on Sprite Dma, but we've only initialized 1 out of 8 sprite pointers, which means the other 7 are of course running the risk of running rogue through the memory as before, if you remember. So that we need to set these to some safe values, simply. That is to say, you cannot just initialize 1 sprite pointer. If you initialize 1, you must set them all. And to do this, we of course continue this. And we're going to call this a Null Sprite. We could either do this, or no, we'll do it this way. It's more familiar. And we'll set all of these to the same address. Hang on, I missed some. I'll fix that later. There we go. Okay, let's check that out. 1, 2, 3, 4, 5, 6, 7, 8. And that's those are all the sprite registers in the Amiga. We need to define, as we did before, we need to define the null sprite. And we actually need to do this as if it were a proper sprite, except it's invisible. So we can put it outside the screen if we want. Let's have a little margin. And that's a 1 pixel high sprite. It cannot be 0 pixels high. That will likely deceive the sprite chip. So this is a 1 pixel high sprite displayed outside our defined display window. And that should get rid of the garbage sprites that it has. So if you want, you can have fun with this. You can draw a little. I wish ASM1 had an insert key to toggle the insert mode. It does not. We can make a little circle. Just make sure the commas are aligned as you draw your little sprite. You can also use IFF converter by Kefrens to get a sprite out. There we go, and we need to duplicate these to get it right. And of course remove the fluff. Like this. And check it. It's 16 pixels high, and we should have a little circle. We're actually pretty lucky that the sprite priority register is set as it is, or it might have been hidden behind the random bitplane data. You can put sprites behind or in front of bitplanes, and you can also insert them between playfields, which is another topic. And you can all the sprites have an internal priority in that sprite 0 is the frontmost and sprite 1 is the next frontmost sprite, and so on. So that's our little sprite, and shall we move it on the screen? Can you guess how that should be achieved? Well, it would be achieved by, for example, adding to this horizontal start position. All sprites are 16 pixels wide. That's why you don't need a horizontal stop position. If you want to make a sprite that is wider than 16 pixels, you'll have to do it the good old way, like on the C64, by simply putting them side by side. Okay, let's move the sprite in the main loop. Each frame it should add 1 to this address plus 1, because add byte 1 to sprite plus 1. And suddenly, woohoo, the sprite is moving. And as you can see, there is a wait here as it disappears at the right margin, because since the horizontal position is 9-bit, there are 512 possible values for this position. We're moving it by 2 pixels at a time, since we're not bothering with the least significant bit of the last sprite control byte. And if you want, you can have some more fun with the sprite, as I have. Just to save you some time, I've edited the sprite. And explain how sprite bitplanes work, and they work the same way as normal bitplanes. They work by combining ones and zeros into a palette color. I've cut holes for the eyes here and set them in the second bitplane. This is the first, this is the second bitplane, so that wherever there's a 1, this plus 2 times the second bitplane 1 bits becomes the color. So this is color 1, all of this. And because bitplane 1 is 0 and bitplane 2 is 1, this is 2 plus nothing, which means that these eyes are color 2, sprite color 2 I should say. And here there's a smile on top of the normal 1 bitplane fill color, which renders these pixels color 3, that is 1 times 2 plus 1. So if you want, you can go ahead and set some colors. I have not prepared this at all, so I'll have to guess some colors. Either way, unlike the normal palette colors that start here with color 0, there is no color 0 in sprites. The color 0 is transparent, and that means that these colors start up here at color 17. Red. And see how horrendous it looks. Green. And blue. And this sets the 3 colors that are used for the first 2 sprites, sprite 0 and sprite 1. 4 groups of 3 colors. And this is the first of that group, so these colors are valid for sprite 0 and 1, and we're just using sprite 0. Enough talk, let's fight. And that looks horrendous enough. Let's see if we can improve that maybe. So we know that the fill color is the first color here. So that maybe we should make it, I don't know, I'm just improvising. And this then is the eye color. And what we make this bright yellow, and let's make a nice white smile on our little fellow here. So that's how it looks. Thanks for listening, and welcome back to the next tutorial.